just walked into the room. So theoretically, you have put on your test right here. You got sorry, not your test. You put on your thing. You got this set up. You found zeros at 3, 1, 2, 3. You got a 0 at -2, -2 at +3. Rolle's theorem says you cannot draw a continuous differential equation that you don't somewhere you don't have a slope of 0. What does that mean? You did it? How'd you do it?
I skewed my graph axes, so I didn't have to have a curve. Technically, I have a linear slope.
Well, if I did this, what would my slope the whole entire time?
0.
So you'd actually have infinite amount of slopes of 0. That would be the converse of the rule, which is yes, you can have lots and lots of them. Can you do it without at least one, though? Well, no. Obviously, if I'm going to start here and end up here, I have to at some point change directions, right? And if I change it to a pointy point, clearly that also is going to lead to a problem, right? So therefore, as long as your continuous differential, there must be a slope of 0 between those 2 points, right? Now, I said zeros because you know what zeros are. But as long as I have 2 points that are the same height, say here and here, there must be a slope of 0 between those 2 points. Agreed?
Yeah.
Okay. Now, why is that important? What do we find at slopes of 0? We find critical points, right? So if you have 2 points that are the same height, you can say there's a critical point between those 2 points. Guaranteed. Has to be one. If it's continuous and differentiable. And if it's differentiable, if it's not differentiable, that would also cause a critical point, would it not? So therefore, Rolle's theorem basically tells you where critical points can be found. It doesn't tell you where they are. It tells you where they can be found. Somewhere between those 2 points is a critical point. I don't know where. There's one. All right? So if I choose a point 1, 2, 4, 2, I already did that part. Did we get that? The second paragraph says down there, if I choose point 1, 2, 4, 2, they're the same height. Therefore, a point between them, there must be a place where the derivative is 0. Got it? Okay, so problems 1 through 4. It asks a very interesting question. It says, explain why Rolle's theorem does not apply to the function, even though there exists an A and B such that f of A equals f of B. So in other words, they found 2 points of equal height, but Rolle's theorem wouldn't apply in this case. Let's look at number 1. Somebody tell me why Rolle's theorem would not apply in this case. It's a pointy point, so therefore it's not differentiable. We've used the phrase, it is not differentiable at x equals 1. That's the way we'd say it for the calculus people. Please do not tell them the pointy point thing. They get cranky. Yes.
So what does it mean differential?
I actually have no idea. That means you can't take derivative at that point. Right? Because the slopes are completely different. Okay, number 2, green. Why is number 2 not subject to Rolle's theorem?
Not a continuous line. Because they're not continuous.
Because not continuous.
Thanks, green.
By the way, it's also not differentiable. Well, I'll go answer it first. It was just a color. I know that. Yeah, never mind. 3, green. Why is 3 not different? Green.
Why is it not different?
Why is that? What? So why is Rolle's theorem not applying in this case?
Because it's in it's those 2 lines to the sides of one particle. I don't remember.
They're absolute value bars, which makes it likely not differentiable. But I would even argue even more so. If you can make the bottom equal to 0, it's going to be undefined. Therefore, it's not continuous, right? So number 3, you would say it's not continuous at x equals 0. It's probably not differentiable, though you'd have to work a little bit harder to prove it's not differentiable. Right.
Wonderful.
Yes, but that means you would say that the point where it switches from one function to the other function would be 0, right? So therefore, it would be not differentiable at 0. All right. Everybody blow through that, and then let's do 5, 6, 7, and 8. What are they asking you to do? It's saying, find 2 x-intercepts. And then show that the derivative f equals 0 must be at some point between those 2 intercepts must be true. Okay? So everybody try number 5, and I'm going to walk you through exactly how you do it. Try number 5. What, Rye?
Can I have a worksheet?
No, you cannot. Wait, who's looking out for you? Amala? What the heck?
Oh my god.
She leaves to the bathroom for 2 minutes and she doesn't get a worksheet? We're in a tough class here. Do number 5. Do number 5. This rate. The easiest way to do that, well, the hardest way to do this would be this. What would be the easiest way to do it, by the way? Graph it. Take the derivative, set it equal to 0. That'll take you 2 seconds, probably, with a function like this. But they said find the zeros, so I'm going to do what I'm supposed to do, which is find the zeros. So that would be, I have to factor this, I get x minus 2, x plus 1, am I right? Which means I would have zeros at x equals 2 and negative 1, agreed? So then it says, show that the derivative must be 0 at some point between, somewhere along the way. So how do I prove that? What do? I write the following. You got to write all this stuff down. You ready? Sure. You're going to write f at 2 is equal to 0. You're going to write f at negative 1 is equal to 0. That proves there's 2 points of equal height. What else do you need for Rolle's theorem? F of x is, f of x is continuous. Continuous. Where does that get continuous from? Negative 1 to 2. Now, you can take something larger because you know it's continuous, so I might go negative 2 to 3 or something, give myself a little extra room. So they can't argue with me later about boundaries. And then f of x must also be what? Differentiable. Differentiable. Negative 2, 3. Now notice I didn't explain how I know that. How do I know that? I know that because it's one of these functions we dealt with about 5 billion times. It's a parabola, right? Fair enough? Sure. Okay. Do number 6 as fast as you can. Should be fairly quick. And then we'll flip this over and talk about miles an hour. Go see your counselor, please. Tom, what do you get? 50 miles per hour. Thank you. 50 miles per hour. Now, 50 miles per hour is a derivative, is it not? Because it's a rate of an original value. Agreed? Strong? All right. Now, MVT says the following thing. The mean value theorem says this. It says you can't start below the average and end below the average without at some point driving the average. So, Mr. Tong, evaluate that sentence, that statement. I'm starting in my garage. I'm driving to Los Angeles. Can I get 400 miles in 8 hours without crossing 50 miles per hour? Okay. So all it says is somewhere along the trip, my average derivative, my average speed, is going to be equal to my instantaneous speed. At somewhere along the trip, these have to be equal to each other. Okay? Could I drive it virtually the whole entire time at 50? Yeah. I could do it one time on the way up and one time on the way down. All right? There's no stoplights, police officers, whatever. Okay? So mean value theorem says the average slope is equal to the instantaneous slope somewhere along the trip. Has to be. Okay? We dealt with this a long time ago. We first started talking about derivatives. I said there is a curve. We had a curve like this, and I don't know what the bounds were, but I said, is there any way to prove that you had to be going at least 7 meters per second at some point on the way? And you went up 8 meters in 1 second. And everybody in the room said yes. And I said, how can you prove that? And then look on everybody's face like, he went farther, faster. What we use now? The mean value theorem says at some point the average is equal to instantaneous. Has to be. Okay? All right.
What's the difference between this and the IBT?
IBT says there's a number in between the two. If you start at 0 and end at 5, you must hit every number in between those 2 points. It doesn't matter if it's a derivative or not. It's just every point, right? Okay. So mean value theorem says no. Now there's exceptions to mean value theorem. For example, Mr. Tong. Actually, this is why I didn't pick on Strauss, because I was afraid Strauss would give you one of these examples. Go Strauss! Here we go, Strauss! Now, I want to violate mean value theorem, so I get in my car. Turn it on. What could I do that might possibly allow me to violate the mean value theorem?
As in, never hit 50.
Never hit 50, but get there 400 miles in 8 hours.
Don't drive your car.
Don't drive your car. How would you get there?
Another car.
Yeah, drive another car. That's lame. You're still going to get going 50 miles an hour at some point.
Oh, go to some undefined speed and then go back to 0.
He's not wrong. This is why we get to call it him. What if I drink a cup of coffee, hang out inside of my car, then push my, what is it called in Back to the Future, my flux capacitor button. I go back in time.
Oh, no.
Then I could get there driving 20 miles per hour, right? And never cross 40 because I teleported in time. My slope would be instantaneously like this. Or if my car can teleport, push the button, I'm in Los Angeles. When was I going 50 miles per hour? I was not. So, the mean value theorem is also limited by the following 2 ideas. It must be continuous and differentiable for this to be true. It must be continuous and differentiable for this to be true. Right? You can't teleport, the car can't be a teleporting car, and the car can't go back and forth in time, therefore making an infinite slope. Right? Right? Make sense, everybody? Okay. Doesn't happen very often in real cars. All right. So, now I'm going to read the instructions for you. Listen carefully. Next exercise 39 through 46, determine whether the mean value theorem can apply. How are we going to determine that? It's different and continuous from the starting point to the ending point. If the mean value theorem can be applied, I want to find all values of C. Guys, this is one of those things where the language kills you. You're like, I know what I'm talking about. I can't get the right answer. I don't understand what this question is even asking. This is it right here. This question is really easy, and you're going to get it wrong. You're not even going to understand why you're doing what you're doing if you don't listen very carefully right now. Okay? It says, if the mean value theorem can be applied, find all the values of C on the open interval such that the derivative is equal to the average. Now, this is the dumbest question ever. AB Central asks this question. It drives me crazy. What are they asking you to do? They're asking you to apply the mean value theorem, which implies you don't know how to find the slope of this thing, right? So you use the mean value theorem to prove the slope happens and what the derivative would be. Now we can prove exists. But then the second sentence is, and then find where it is. Well, if you find where it is, why would you use the mean value theorem to begin with? What's the point? If I want to find where the derivative is 3, I can find that like that. I just take the derivative, right? So this is a weird situation. So when mean value theorem is powerful is when you have 2 points in space and you want to prove that the derivative is something between those 2 points. Does that make sense? But you don't know what the function in between is. It's doing something weird. Okay? That's when you use the mean value theorem. But in our example problems, when are we going to use it? Functions we can already take the derivative of. So this is going to be kind of weird. So here's what I want you to do. I want you on problem number 39. I want you to do the mean value theorem, just like written. Tell me what the slope would be between those two. At least one place, the slope would be what between those 2 points. Try that out first, and then we'll talk about the rest of the instructions. Okay? So try the mean value theorem.